Hello and welcome back. In this video, we're going to derive one of the two equations we'll be using when we study fluid dynamics. Fluid dynamics are fluids in motion. So this equation that we're going to be deriving is called the equation of continuity. And what we're going to do is begin by just looking at a pipe. So you can see that this pipe, the flow is coming from the left. This pipe of area A1 with fluid speed V1 tapers down to an area A2 with a fluid speed V2. This derivation is going to be centered around conservation of mass. Notice that I have enclosed a mass M1 that is contained in this wider section of the pipe, and as this mass M1 moves this distance x1, an identical mass must move down the pipe. So this mass M2, which occupies the pipe of area A2 and length x1, this mass M2 is the same as this mass M1. So this is conservation of mass. So M1 is equal to M2. I can re-express mass using our equation density is equal to mass divided by volume. If I rearrange that, I can rewrite mass as density times volume. So M1 can be written as rho 1 V1, and M2 can be written as rho 2 V2. In addition, I can re-express the volume. Notice the volume that confines this mass M1 is the cross-sectional area A1 times the height of that cylinder, x1. A1 x1 is V1. And V2 is a cylinder as well. Its volume can be written as the area A2 times the length of that cylinder, x2. So there is the volume V2. Now if I divide both sides by time, because as this mass M1 moves this distance x1, an identical mass M2 moves this distance x2. So I'm going to divide them by time. And when I do, I'm going to organize it so that x1 is directly over time and x2 is directly over time, so that I can re-express x1 divided by the time as the speed v1, and I can re-express x2 divided by the time as the speed v2. So now taking this and rewriting it, I can write rho 1 A1 V1 is equal to rho 2 A2 V2. So this is the general equation of continuity for all fluids. But now if we tailor to incompressible fluids, as we're going to be focusing on at this level, incompressible fluids are liquids, then I can set rho 1 equal to rho 2 equal to rho. In other words, the density doesn't change from this location to this location. The density of the fluid remains a constant. So that rho will cancel on both sides of the equation for the incompressible fluid, and I'll just have A1 V1 equals A2 V2. So this is the equation of continuity that we're going to be using for liquids. And notice here what this is telling us, that is where the tube is wide. So let's say A1 is greater than A2, as is in our drawing over here, then the speeds must have an inverse relationship. So the fluid is moving slower at the wider part of the tube than it is at the more narrow part of the tube. If instead A1 is smaller than A2, the opposite of this scenario, then the speed again has to have a different relationship. So because of this equality, when we look at comparing the areas, if A1's bigger than A2, then V1 must be bigger than V2 and vice versa. So here's the equation of continuity. In the next video, we're going to derive Bernoulli's equation, and these two together will provide us the two equations that we will use as we look at fluid dynamics this semester. We'll see you next time. Thank you.